right, we are starting our recording. Can someone grab the lights for me, please? Thank you, Zach. Yes, we are recording from ninth period today. I think one will do it. So we have a lesson here today about vision. We are continuing our discussion on vision. And with that, we can recap on the different parts of the eye. Yesterday, we learned about the protective outer layer of my eye, which is? It is my cornea. Very good. So my cornea is the protective outer layer. Yes, Sarah? The eye patch? Yes. Sarah is making a comment right now about seeing a student who did in fact damage her cornea and was wearing an eye patch. So yes, scratching your cornea is very, very painful. Now, part of having a cornea is to protect a hole which is in your eye, which is known as my... Yes, that is my pupil, and the purpose of the pupil is to allow light to come into my eye. The amount of light is regulated by my... It is regulated by my iris, which is a, what kind of tissue? Very good. It is a muscle. So my iris is going to allow so much light to come into my eye at any given moment. And so I can see things like Sarah on her phone right now that is creating an image that is coming into my eye. The light comes into my eye and it hits something directly behind my pupil, which is my... It is my lens. What does the lens do? The lens will flip the image, yes. What else does it do to the light that is coming into the eye? It will project it to the back of the eye, yes. It will also bend the light in a process that is called refraction. Very good. So the light becomes refracted by the lens, and the image that hits the back of the eye is going to be upside down. But we don't see an upside down image because it is the occipital lobe that will turn it right side up again. It's going to protect that, or excuse me, it's going to project that image onto the back of the eye, which is known as my... It is my retina. Very good. And what is so important about the retina? Very good. It is going to be the area of my eye that completes sensory transduction, which is... What happens in sensory transduction? Yes, AJ. Very good. So in sensory transduction, what I am doing is converting one form of energy into another form of energy. And in this case, I am converting light energy into an electrical impulse because that is what my brain is capable of understanding. It doesn't understand light, but it does understand electricity. What else does my brain understand? It understands chemicals. So because it understands electricity and chemicals, I have to do sensory transduction with my eyes, and what other sense? Hearing. I have to do it with hearing. So why don't I have to do it with smell and taste, for example? Because smell and taste are not going to require sensory transduction. Yes, AJ. Very good. So when it comes to eating or when it comes to smelling, I am ingesting chemicals and my brain automatically understands those. So sensory transduction isn't something that I need to do here. So because of that, it's actually much less common for people to have problems with tasting or smelling, but more likely to have problems with vision or hearing because it's a more complicated process and there's things that are more likely to go wrong with my vision or my hearing. So today we are going to be focusing more on the retina, but with that we need to quickly discuss visual acuity. So many of you have problems with vision where you cannot see far away or you cannot see things up close. And when you have a problem with vision, it is referring to your visual acuity, so how well you can see. The majority of people have problems with seeing far away, and this is referred to as nearsightedness. Nearsighted because you can see things that are near you. So being nearsighted means that I can see things that are near me. So I cannot see far away. So most people, particularly if you have a visual deficiency, early on in life, you're going to have a problem with seeing things that are that are far away. Not being able to see something that is close to you, or rather being capable of seeing far away, is referred to as farsightedness. Is being farsighted. So being farsighted, I can't see things that are close up. And as we age, most people become farsighted. This is why your parents, like when you go out to a restaurant, you might see your parents take that menu and they hold it at arm's length and they look kind of down at the menu, sort of funny. That's because it's indicating that they are becoming farsighted. So there's a couple of reasons why your vision can become deficient. One has to do with the lens of the eye. So this is my lens right here and the refraction that it creates. And that in some people the lens itself is deficient. But for many people, one of the reasons why they have problems with their vision is because of astigmatism, or that their eye is essentially misshapen. So if your eyeball is longer than normal, that's going to result in nearsightedness. So what happens is that you have the, again, candle image. The candle image is going to enter into my eye, and the correct candle gets reflected before it hits the retina. So because it's hitting it before it hits the retina, the image that does in fact hit the retina is out of focus. So what your brain picks up is essentially blurry because the lens is giving you an out of focus image. Likewise, in people who are farsighted, this image has to do with farsightedness, and that what you see here is that the image, the eyeball essentially is shorter than normal, and so the correct image is getting reflected beyond the eye. So then what does hit the retina is again an out of focus image. Does that make sense? All right, very good. Are we good to move on? Yes? Okay. So like I said, our focus today is really going to be on the retina of the eye. And the image that we have here is, this is a blown up picture of the retina. So you can see here that it's identifying this little outlined area. And so this is a blown up image of the retina. What would we call this area right here that is directly across from the pupil? What would this area of my eye be? Yeah, very good. This is my fovea. And what is the fovea? Very good. It's my central point of focus. So it is easiest for me to see at the fovea. It's easiest for me to see at the fovea, which is directly across. What would this area right here be called? Well, yes, it's my optic nerve, but we have another thing that we call this area right where the optic nerve is entering into my eye. Anybody know? It is my blind spot. Very good. It's a blind spot. Why is it a blind spot? There are no thingamabobs there. Yes, that would be correct. And by thingamabobs, we are referring to rods and cones. So in class, we identified that our retina has 3 layers of cells. And the first layer of cells are my rods and my cones. And my rods and cones are what actually does the sensory transduction. So this is what literally creates the neural impulse from light. That is the job of these rods and cone cells. So from there, that neural impulse is created, and it goes to this layer of cells, which is my bipolar cells. This layer of cells, which is my bipolar cells. My bipolar cells will then be attached to the third and final layer of the retina, which is made up of ganglion cells. And it is the ganglion cells that rope together to then form my optic nerve. And then my optic nerve is going to be connected to what part of my brain? Very good, my thalamus. It's going to be attached to my thalamus, which then is going to relay the information to my occipital lobe. Very good. So my optic nerve goes back to my thalamus, connecting it to the occipital lobe. Why, again, I have a blind spot is because there are no rods and cones where the ganglion cells have converged and left the eye to form the optic nerve. So again, my retina is what is responsible for sensory transduction. Someone earlier today mentioned having a detached retina. That would be very problematic. It's where this back portion of the eye literally does become detached. If you are unable to then reattach it, you would lose your sight in that eye. So through surgical measures, you could potentially reattach the retina to the back of the eye, but again, you'd have to do that rather quickly. All right, so again, talking about the retina, and the most important part of my retina are my rods and cones. So my rods and cones as cells that create sensory transduction. Rods and cones are going to have a very specific task or duty in terms of how they create sensory transduction. So first of all, in our image here, my rods are being displayed as these blue cells, and my cones are going to be the yellow cells. So you'll notice right off the bat that I have way more rods than I have cones. So I've got a lot of cones, I have a lot of rods in comparison to cones. My rods are what allow me to see black, white, and gray. They allow me to see black, white, and gray. And they work in what we refer to as twilight conditions, meaning that when it is rather dark and I have very little light accessible, that is when my rods are going to be activated. So my rods work essentially in the dark. I have to have some light because there has to be something for me to see. But my rods are what allow me to see black, white, and gray. So like if you wake up in the middle of the night and you have to go to the bathroom, and of course it's all dark in your house. If you wake up and you see like a pile of laundry on your floor, you probably cannot differentiate between different pieces of clothing. All you see is like a big blob of clothing. And that's because you're using your rods. Your rods don't allow you to see very well, but primarily they allow you to navigate around the world so again that you can survive. So your rods are allowing you to see in this twilight condition because they allow you to see black, white, and gray. And again, it's why you cannot see colors in the dark. That your different types of piles of clothes, it's just one pile. Your cones, on the other hand, are what allow you to see colors. So cones equal colors. Cones equal colors. Cones allow me to see colors. They also allow me to see more clearly, or they give me clarity. They give me clarity. So cones equal color or clarity. And here's the reason why. So if you look in the image, you can see that there are 5 rods attached to one bipolar cell. Whereas the cones, they get their very own bipolar cell. And because there's less interference, if you will, it's the reason why you can see more clearly with your cones. You can see more clearly with your cones. and cones give us color. Now, in order to see color, though, I have to have light. So light is what allows my cones to be activated. So knowing this, where do you suppose, if I were to look at my eyes straight on, where would my cones be located in my eye? Yes, they're in the back. I mean, they're on the retina. But where on the retina? Where would I find the majority of my cones on my retina? Why would I find them at my fovea? Exactly. Why is my fovea the central point of focus, and why do I see the most clearly at the fovea? Because that's where my cones are, and my cones are what allow me to see clearly. Also think about how the iris and pupil function. That my pupil is rather small when there is a lot of light, because the light is what is activating my cones. What happens to your pupil when it's dark? It dilates, it gets bigger. So then where do you suppose your rods would be located? Exactly, they're farther away from the fovea. So my cones are concentrated at the center at my fovea, and then my rods are further out. So the reason why your pupil dilates not only is to allow more light in when it's dark, but it's to also activate those rods so that you can in fact see in the dark. Another aspect of vision worth mentioning is something called feature detection. Feature detection is a development that was created by or discovered by psychologists Hubel and Wiesel. And what they discovered was that my vision is way more than just seeing. There are multiple layers to seeing or different features to vision. And that people can have deficiencies in one or more of these features. So feature detection is this idea that I have clusters of neurons in my occipital lobe that allow me to see specific parts. And so, for example, one of the specific parts that I can see are edges, or lines, or angles. So, like in this image of a face where there are different angles and lines to the face, I am activating different feature clusters in my occipital lobe. Another feature detector is movement, so being able to detect movement. So the other day when we were watching Crash Course, they mentioned Oliver Sacks, who was unable to detect faces. That's because his feature detection for facial recognition was damaged. I know of another case where a gentleman was blind, but he could still detect movement. He couldn't tell you what was moving, but he would be able to tell you the direction in which something was moving. And so because of that, he's identifying that he still has one of his feature detection areas in his occipital lobe able to work, but the other types of feature detectors where it would be like angles or lines or even colors, those were completely gone in this particular individual. We also see this in different types of animals. So like, for example, frogs, their vision is not very good except for movement. And so because of that, if you create like an image of a frog in your head where it's like sitting on a lily pad and it's going to stick its tongue out and grab a fly out of the air, it wouldn't be able to do that if the fly wasn't moving. Where you could take a frog and have it surrounded by flies, and it would starve to death if those flies never moved, because it cannot sense it without the movement. It can't see it without the movement. So again, another aspect of feature detection. So knowing this, we also come to color vision. So we know that cones are what allow us to see colors. But what colors are we able to see from these cones? And so with that, I want you to think about if you have ever had an art class where in your art class you made a color wheel. So if you made a color wheel in your art class, what colors did you use to create your color wheel? What are your primary colors in paint? Very good. They are red, yellow, and blue. So you take red, yellow, and blue, and you mix them together and you make your color wheel. Now, if you were to only have red, yellow, and blue, and you mix those together, what color would you get with your paint? I'd get black, or I'd get a brown. The reason for that is because this is a type of color mixing called subtractive color mixing, where I'm taking away color to the point where I'd have no color, and that's where I get that brownish black. But light is different, and that the primary colors of light are not red, blue, and yellow, but rather the primary colors of light are red, blue, and green. And when I combine red, blue, and green, I am doing what's called additive color mixing. And that my additive color mixing, if I were to mix my red light with my green light with my blue light, is it would give me white light. So if you were to do theater, for example, and work in lighting for a theater, you have red lights, you'd have green lights, and you'd have blue lights, and you could combine all of those to get all the different color lights that you would potentially want in your theater show. And if you were to combine all of them together, then you would get white light. So we know that it's my cones that allow me to see colors, but what about the cones themselves? And this is where we come to something called the Young-Helmholtz trichromatic color theory. And this is a theory that you actually have different cones to see different colors. But anyone want to take a guess at how many different cones we would have based on this theory? No, it would just be 3. That I have 3 cones. What color cones would I have? Red, blue, and green. So the Young-Helmholtz trichromatic color theory is going to tell me that I have red cones, blue cones, and green cones. And that in order to see Brooke's yellow sweatshirt, what would I need to do? What cones would I use? Very good. So looking at Brooke's yellow sweatshirt, I'm actually activating both my red cones and my green cones to show me yellow. And so this is how I get my different colors, is by combining my different cones in my retina. Which then brings me to color blindness. But blindness is really a misnomer, because blindness says that I cannot see color, and that's not true. It's a better description to say a color deficiency. I am deficient in a color, meaning that I don't see the color as well. Because a person who is colorblind often can see color, they just can't see color as well. And the most common type of color blindness or color deficiency has to do with a problem with either my red cones or my green cones, where my red or my green cones don't function properly. And so because they don't function properly, I don't see red the same way that you would see red if you had functioning red cones, or like you wouldn't differentiate between red and green. And really, this isn't a big deal. I mean, colors are beautiful and vibrant, and they bring richness to our lives, but in many ways it's not problematic to not see colors, except when I'm doing something. Driving. Yes, when I'm driving. Ah, yes, because of stoplights. Well, yes, I mean, my red and my green on my stoplight aren't in the same location. But if it's dark out and I'm rather far away and I need to make a judgment call about do I slow down because it's stopped or do I keep going because it's green and I have a red green color deficiency, that can be incredibly problematic. So I don't know if you have noticed, but modern stoplights, so stoplights that have been recently installed, probably within like the past 10 years or so, actually have a little bit of what color included. Anyone know? It's blue. That if you look at the green light, newer stoplights have added a bit of blue to them. And the reason for that is for people who are red green color deficient. That in order for them to continue to be able to see and to know that this is a red light or this is a green light, we've added some blue so that you can differentiate between those colors much better. So, like in these images here, most people are going to be able to see the 25 because the 25 is identifying that blue cone. But the rest of the numbers, and I know it's a little difficult to see in here, if we turn the other light off, you might be able to see it a little bit better. Because like the 6, for example, is kind of difficult to see. That's this one down here. That for some people, you wouldn't be able to differentiate anything between these two dots. And again, that is because of that color deficiency. One last part of color theory. So we have the Young-Helmholtz trichromatic color theory. Another color theory is the opponent process theory. And the opponent process theory is going to tell us that, yes, I have red cones, blue cones, and green cones, and then I have black and white and gray rods. But when I look at something, for example, that is red, I'm actually turning off my green cones because that is its opposite. And so that is actually how I see colors, is by turning off some cones and turning on some cones, or their opponent process, their opposite. One way that you can detect this is in this image right here of the flag. You can see it a little bit better in your textbook because using a computer screen or using a smartboard, because there's light in it, it doesn't work as well. But if you were to go home and you were to look at this image in your textbook and you stare at it for quite a while, and then you look away and you look at like a white surface and maybe you blink a couple of times, what are you going to see? You're going to see a British flag. Yeah, you're seeing what's called an after image. An after image is like when you have your picture taken a bunch of times with the flash and how you keep seeing the flash. Or like if you look at the sun and you keep seeing a dot from the sun in your vision, you're seeing an after image. One of my favorite after images is when I go to the eye doctor and how they will run the light back and forth in your eye. And when they're finally done and you look away and you blink, you'll see like squiggly lines. You know what you're seeing? You're seeing your blood vessels. You're seeing the after image of your blood vessels. How cool is that? I'm going to give you a series of tests in a few weeks, and one of those will be looking at an after image. So opponent process theory is that you have these opposing retinal processes that you're turning off some cones and you're turning on other cones, and that's how you see your color vision. Yes, Taylor. It's because the cone is deficient. So Taylor asked about why some people don't see certain colors, and it's a cone deficiency, that those cones don't work as well. Another point to make is that the majority of people who are colorblind or have a color deficiency are male. And along those same lines, research has shown that women will often see more color hues than men, and it's theorized that women have more cones than men do. And so if women have more cones, then what you're identifying is that women tend to see, greater amounts of color. And one way that you can tell this is if you get a man and woman together and they start arguing about periwinkle. You know the color periwinkle? periwinkle is kind of like a blue purple color, but men generally only see it as blue. They don't pick up any of the purple tone to it, and that's because the purple requires that red cone to be working, and again, that men generally don't have that same kind of color vision. So I'm going to stop our notes here, but I do have a video that I want to share with you, and you can see that in your Google Classroom.